Hey AP Calculus students, welcome to your very first calculus video. In this video, I want to look at this question. What is calculus? A lot of people sign up for this class and have no idea what calculus is or what it is about, which is fine because how would you know? Because you've never taken this class. Lots of people out there take calculus, they study calculus for a long time, and they have the feeling that it's a bunch of formulas and equations and formulas that we have to memorize, and it doesn't make sense because they never had a framework of understanding explained to them. And by the way, certainly there are a lot of formulas and equations, and in a few short months, these things in front of you, you will be able to make perfect sense out of and tell the story of what's going on there. So what I want to do today is build a file cabinet in your brain. It's going to have 3 sections, just like our picture, and it's going to give you a framework for understanding the story of calculus that you will be learning all year long. But before we do that, I'd like to make a quick word about our administrators' doppelgangers. I mean, come on, do these guys not look like our administrators? I think it's the noses. Yeah. Right, so these are not our administrators. These are the gentlemen who were credited, or are credited, with the development and discovery of calculus. Unlike all of the other math that you have studied in your life, calculus is not ancient. So all of the algebra, and all the geometry, and all the trig, and all the algebra 2, and all the pre-calc, all that stuff had roots back in ancient Egypt and ancient Greece. And actually ancient Babylon as well. I don't know how to draw Babylon. Right, so back to these guys with the sweet hair. What's interesting about their work is that it was happening in the late 1600s. So relatively speaking, everything that we're going to look at this year in this class is new. This is new math. Calculus is new math in the scope of human history. And also worth noting is the fact that both of these guys, Newton and Leibniz, were developing ideas at the same time. They were not working together, but they were developing ideas at the exact same time. And those ideas would ultimately become the calculus that subsequently changed science and mathematics. So there's a big controversy around who gets the credit because they were both developing ideas at the same time. So different people have different opinions. Did Newton discover it or did Leibniz? And they've got slightly different approaches, but they were both discovering the same thing at the same time, which is crazy. So let's move into this file cabinet of ideas. There are 3 big ideas in calculus, and everything that you learn starting today is going to fit into either file cabinet A, file cabinet B, or file cabinet C. And as this year goes on, you will become articulate in explaining the connections between each one of these file cabinets. So file cabinet A. File cabinet A is the world of limits. We are going to use limits as a foundation from which to understand file cabinet B, which is derivatives. Whoa. Come on, iPad. Right. And we're also going to use file cabinet A to understand file cabinet C, which is the world of integrals. So these are the 3 categories, the 3 big ideas that we're going to be looking at all year long. Everything will fit into one or the other of these 3 cabinets. So I want to take our remaining time and give you a basic rundown of what the big idea is in file cabinet B and file cabinet C. And for now, I want you to just think about file cabinet A, which we're going to start talking in depth about tomorrow, as the foundation for the other two. File cabinet B and file cabinet C are each associated with a specific problem. The tangent line problem and the area problem. So let's take a look at those. So since you were in middle school or maybe early high school, you have been talking about linear functions like f of x in front of you right now. This is a linear function because it's a straight line, and as soon as you see a function that is a straight line, you should automatically be thinking about one of the main attributes of that line, which is the slope. The slope is a really big deal. You've been talking about the slope for lots of years. And what the slope is the change in y, here's my y-axis, divided by the change in x, which is the x-axis. It is the relationship between the y direction and the x direction. So you know that if you want to find the slope of a line, you do this simple thing called rise over run, because the y direction is associated with the with rise, and the x direction is associated with running side to side. So if you want to find the slope of this line, my picture is not very accurate, but let's say that this is 1/2. And this is cool because this tells you stuff. This tells you the relationship, like I said, between this variable and this variable. So if this is time and this is distance, if you know the slope, you can talk about your speed. You can talk about how quickly you are moving. That is what a slope is. In other words, this is a rate of change. And this is something that should all be super familiar to you. Rates of change are very powerful. Oh, come on, iPad. They're very powerful for a lot of reasons, but certainly at this point you know that in the world of science there are tons of manifestations of this idea in the natural world. But here's the problem. Most things that occur do not happen in a linear fashion. So linear functions take up a tiny, 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 tiny little corner of what we know of the world of functions. Quadratics, exponential functions, logarithmic functions, polynomial functions, these are all curves. So what the derivative problem is interested in answering is the question of what is going on in terms of the rate of change I'm really struggling here. What is going on in terms of the rate of change on a curved function? The problem is, how can we talk about that? Because the rate of change here is different than the rate of change here, which is different than the rate of change there. If you were talking about the speed, you could agree, hopefully, that you're going kind of quickly here, and maybe here you're not really moving at all, and maybe here you're doing something different. So what we are interested in talking about is what is going on at a particular moment in time, at a particular instant. Or in other words, what I want to know about is what is the instantaneous rate of change. So I've just given you your first idea of the derivative. This is the derivative. A derivative is an instantaneous rate of change. So what that means for us with our graph is that if we zoom in and zoom in and zoom in and zoom in and try to ask ourselves what's going on at this instant, we need some way to talk about the rate of change at this point. And this is why this thing is called the tangent line problem, because what we can do is approximate this curve by a straight line that touches at exactly just one point. The definition of a tangent line is that the line touches a curve at precisely one point. So what we do is we take a tangent line and we just put it along the curve and we find the slope of this thing. We can find the slope of a line because we've already talked about that, rise divided by run. This is category B. This thing has all kinds of manifestations, but this is the really, really, really big idea of category B. This is the world of derivatives. Again, we care about limits because our understanding of limits will tell us how to solve and how to understand derivatives. And also how to understand and solve integrals. So let's talk about integrals. Prior to the 1600s, humans were incapable of answering this question. For some function f of x, what is the area, the precise exact area underneath this curve? How on earth could we do that? And the answer is with an understanding of limits. And I'm going to explain more of this, obviously, as time goes on. But this is the problem that motivated the development of integral calculus. The area problem, finding the precise area underneath any curve, underneath a polynomial function or an exponential function or a logarithmic function. And you should be wondering at this point, why the heck would you want to know that? And that's good. That question will be a big part of what we talk about in the coming weeks and months. I hope you're on board. I hope you're feeling awesome. And I hope that your understanding of these two problems, which is very basic at this point, but I'm hoping that the description of these two problems creates for you a file cabinet in which you're going to put all of the information that you ever run across this entire year into.